Hey guys, so this is an example of a related rates problem, so this will be with volume. So here's the situation. A conical tank is being filled with water at a rate of 45 meters cubed a minute. The tank is 40 meters tall and 10 meters wide. How fast is the water level rising when the water is 15 meters deep? And I just realized I forgot this. Let's say that the tank is tipped down. Okay, so here's what I want to suggest. I want you to actually pause the video here and hit play when you're ready. So draw the situation and also figure out what is the equation that kind of would model this, and then hit play. Okay, so conical tank and the tip is down, and so there's a few numbers kind of that we see here. So it's 10 meters wide, it's 40 meters tall, and then the water, we're talking about a moment where the water is at 15 meters deep. So the situation that's going to kind of relate all of this is going to definitely be just this volume formula for, a cone. And so now we have to start thinking about how to approach this. What are we actually interested in here? What numbers do we need to fill in? So one thing I usually suggest is when you look at your formula, the first thing you want to do is figure out what is changing in that formula. So with the way that this problem is written, is there anything that stays constant? The water level is just going to keep rising, which means that the height of this is going to change, and then also the radius is going to change because we're moving up along the cone. So both R and H are changing, therefore so V is also going to change, so we don't have to fill in anything as a constant. So it might be helpful to take the derivative at this point and just kind of see where we're at and then kind of figure out what to do from there. So when I take my derivative, so remember that you want to keep this in terms of whatever rate you were given. So this is talking about meters a minute. So we need to now take this physical situation, and when we take the derivative, we need to take it with respect to time because our rates are within minutes. So keeping that in mind, if I implicitly differentiate, this is going to be dv dt equals, equals 1/3 pi times 2rh dr dt plus 1/3 pi r squared dh dt. So I had to use the product rule here because I've got r squared and h. And I just want to take a second to think about this. So what information could I actually fill in? So I want to check that off. So dv dt, that was actually given up here, so that one's good. Now, r and h, I know what h is, so we're talking about a particular moment, so we want to talk about the moment at 15 meters deep. So that's going to stand for my h. So I've got my h, and then from this, it's going to take some work, but from this, we can actually see a similar triangle with kind of this and this one. So we can also figure out our r. So the r is good to go. Which leaves me with two rates here, dr dt and dh dt. So rereading the problem, notice what the problem is asking for. How fast is the water level rising? So this problem is not even asking me about dr dt, it's talking about rising, which is dh dt. So I have this extra rate now that I don't have any context of how to solve it. And by the way, you cannot use like the Pythagorean theorem, or you can't use like a similar triangle to figure out a rate. Your physical situation has nothing to do with your rates. You need some sort of context for that. So I went through all of this just to explain that sometimes when you take your derivative, you're going to find that you might actually have more variables than you needed. And when that happens, you have to come up with a new approach for the problem. So basically now we need to figure out how do we get rid of having dr dt. And if I think about just a general strategy for getting rid of dr dt, it would sure be nice if I just got rid of r, then I wouldn't have to take the derivative with respect to it. So can I rewrite this formula without an r? Well, now I can start actually thinking about kind of the context of triangles here. So let me maybe redo this without the water in it. And I'm trying to set this up with something to do with r. So instead of having this circumference of 10, why don't I get rid of this now and let's just call this 5, and that sets me up to now kind of make a relation with r. And your first thought might be, okay, and now what I'm going to do is I'm going to set up this as 15, and then I'll figure out what the radius has to be in this situation. And maybe you would then go, oh, now I've got 40 over 5 equals 15 over r, and now I can solve for this. There's actually a problem with this approach. So you don't want to do it like this, because this would indicate that r is a constant, and r is not constant. So that's something I talk about in my lesson video version of this. So if you want to see that in more context, you can watch that other video. But basically, if r is changing, we need to make sure that we're not tying r to a particular number. We want to make sure that we set this up to allow r to continue to change. So using numbers will not work. So we need to be more general. And so the better way to be general then is to just set this up as plain old r and h, because this will then allow me to eventually get an equation that where I can substitute out r but still kind of allow it to change. So I can set up my similar triangles. So this is 40 over 5 equals h over r. And remember, our goal was to get rid of r, so let's actually just solve for r. So this is going to be 40r equals 5h. So r is going to be 5h over 40, or h over 8. Okay, so this is great because now I have r in a context where it can continue to change, but I don't need it in the equation anymore. And now I can just substitute this in for my r. So let me clear this out. And let's restate this equation now as 1/3 pi h over 8 squared times h. So now I can restate this entire equation as, so let's see, this becomes h cubed over 64. So then I can rewrite all of this as pi over 192 h cubed. So now I have a much better equation to take the derivative of. And again, we had to do this because of the context. It's because we had that extra rate. So now let me clear some space and we'll take a derivative again. So I take the derivative of v with respect to time. That'll be dv dt. And then this will be pi over 192 times 3h squared dh dt. And that is a much simpler equation now than what we had before when we just took the derivative of this. And now I can say, oh, I can plug in 15 in for my h, and I already know what dv dt is, and so all I'm left with is dh dt. So now I know I've done this right. So I can fill in my numbers. So this becomes 45 equals 3 pi over 192 times 15 squared dh dt, and I'm running out of space, but if I sort all of this out and I solve for dh dt, I get 4.07 meters a minute is what that will come out to. And so now we've got our rate. So that's how you would troubleshoot that. So that wraps up this example. I'm not sure if you guys actually find it helpful for me to explain why to approach it one way versus the other. So if you leave me a comment, I can always redo the video just kind of plowing straight through the solution. But I think a lot of times people struggle with just why some of these don't work out. So any feedback you give me would be really helpful. Thanks for watching, guys.